Hello, hello, hello. We're going to be talking about kinetics. Again, somewhat of a review, but kinetics are a study of reaction rates, right? So we did this in general chemistry. Now we're going to talk about it in OChem. So here's a general diagram for you, and we have two curves, red and blue. These are the two activation energies for each of these. And as we know, the activation energy is basically has an effect on the rate. So the larger the EA, the slower the reaction rate, right? So it takes a lot more energy and time to climb that hill. But another thing is the higher the concentration, the faster the rate. And this is related to collisions, right? More collisions, the faster the rate. Higher the temperature, the faster the rate as well, because we're going to have more kinetic energy, we're going to have more collisions, and all leading to a faster reaction rate. So there's a couple other things I want to add, and that is just some fun stuff about organic reactions in general related to activation energy. Most of them are at within 40 to 150 kilojoules per mole. Okay, so what does this really mean? Well, activation energies that are lower than 80 kilojoules per mole will actually readily occur at room temperature. Okay, and activation energies above 80 degrees will require heat. Okay, so remember that triangle represents the heat over the reaction arrow or under the reaction arrow. Now, a fun little fact about 10 degrees increase in heat actually doubles the reaction rate. So that gives you an idea as to how temperature and energy and activation energy are all related in terms of reaction rate. Okay. Now, delta H, delta G, KEQ, they are not to be kind of lumped in with the activation energy. So they're only related to the equilibrium and the energy of the reactants and the products, not the rate. Okay, so it's really important that you don't lump them all together. That's why those were all thermodynamic processes, right, or concepts. Okay, so excuse me. So a multi-step process. We have a rate equation. Hopefully you guys remember rate equations. Super fun stuff, right? And the rate equation only has the concentration of the reactants from the RDS, the rate determining step. Remember, that's the slow step. The one that takes forever, the one that generally determines the overall rate of the reaction. Okay, so the rate is equal to K, the rate constant, times the concentration of the reactants, right? Now, if it's a fast reaction, then we are going to have a large K value, a large rate constant. If it's slow, we're going to have a small rate constant. If it's a fast reaction, we will have a low activation energy. And again, slow reaction is high activation energy. So let's take a look at what we mean by the multi-step process and having the concentration of the reactants from the RDS, the rate determining step. So bimolecular versus unimolecular process, that's basically, here's an example of a reaction. Now we have AB plus C that attacks, and we form the products, right? And so that rate is equal to K times the concentration of AB and C, because both of those are involved in making the new product, and it's only one step. We can also classify this as a second order rate equation because you add up those exponents, which are 1, and you get 2. So that's second order, okay? Now, related to that multi-step process above in the rate determining step, we have AB it splits up into A and B separately. Then you combine it with C to make BC, compound BC. So here's the mechanism, what it looks like, okay? Now, this is a two-step process, right? We have step 1 and step 2 here. Again, relating, this is that blue text is what we're referring to here. And AB is the slow step, and that there is why we only have the concentration of AB in this particular rate equation, which means that we can add as much C as we want in there, but it will not affect the rate of the equation. So we talked about concentration affecting the rate of a reaction above, right? Well, in this particular one, we can add more C or more AB, and that will affect the rate. But in that two-step process, we can only add more AB to affect the rate of the reaction, okay? And since we saw in the one-step process and the two-step process, the different reagents coming together and only a certain scenario where, like the two-step process, only the addition of the AB affected the rate of the reaction. So that allows us to actually ID mechanistic pathways, okay, and which is really cool. So let's take a look at some practice problems, to kind of give us a better understanding of what we're talking about. So if we have bromoethane, a hydroxide, and we are given a rate, what we want to do is, we're given a rate equation. I'm going to give you 3 different scenarios, and I want you to determine what the scenarios are what effect these scenarios are going to have on the overall rate of the reaction, okay? So tripling the concentration of bromoethane, hydroxide, or both. And then this one right here is just an equation, or more or less a mechanism. It's a reaction scheme, and I want you to determine what the rate equation is based off of this, okay? So pause the video right now, and then let's see if you can get what I get, okay? Okay, so part A, triple the concentration of bromoethane. How does that affect the rate? Well, since we have concentration of bromoethane, that factor, or that variable, whatever it is in the rate equation, if we triple it, we are tripling the rate overall, okay? And then if we triple the concentration of hydroxide, we do have that term in the rate. So if we triple it, we will triple the rate of the concentration. Since we have both of them, if we triple the concentration of each of them, that's multiplying 3 by 3, which is 9. So it will increase the rate of the reaction by a factor of 9. Now, for A, since we have a one-step process on this, the rate is dependent on the concentration of bromopropane and hydroxide. So we'll put the concentration of each of these here next to the rate constant, whatever that may be, and that's the rate equation. So since this second one actually has what the slow reaction is, then we know that that would be the rate determining step. That's really all the rate determining step is. It's the slow portion, and so this bromo chicken foot is our reactant of interest, and that's the rate equation, okay? All right, so now what we get to do is work on catalysts and enzymes. So they're pretty much the same thing. But catalysts, hopefully you remember from general chemistry. If not, it's cool, but they speed up a reaction rate, okay? And they do this by lowering the activation energy. And another definition of, or an additional key, is that a catalyst is actually recovered unchanged at the end of the reaction. So usually a catalyst is put in a chemical reaction in very small amounts because it's kind of reformed in the end. So, for example, if you have a reaction with an acid catalyst, you can literally put a drop of acid in there and it can promote the rate of the reaction or increase that. So I've highlighted the OH and the H here to show you where they are in the end, the product. They form water. This blue oxygen is the blue oxygen in the ester product, but notice the sulfuric acid or the H plus aren't really showing up on the left side or the right side. They're just reformed and you don't see them as a product, okay? Now this alkene plus H2, this is actually done with palladium catalyst to form the hydrogenated product. This is the similar way that hydrogenated oils are formed, which we'll go over later in the semesters. But palladium's a catalyst and you don't see it in the products form, okay? So delta G, delta H, K, Q, remember they don't determine the rate of the reaction, they just the equilibrium and like the concentration of the products and the reactants at equilibrium. Catalysts do affect how quickly the equilibrium is achieved, okay? But they also don't really affect the concentration of the products or reactants at equilibrium, okay? They just have an effect on activation energy. So as you can see here, determine the rate, that's activation energy, right? So they're not related. Remember, the thermodynamics and kinetics, two different topics. Okay, so what I want to draw you is an energy diagram for a given reaction. And whoops, let me make these, the reactants and the products are going to be the same thing in this case, okay? So we have a red reaction and a blue reaction. That red reaction is a catalyzed reaction, and then the blue reaction, or diagram, I guess, is the uncatalyzed reaction, okay? So you can see that the activation energies are different, the red being lower and the blue being higher. So if it's a higher activation energy, then it's a slower reaction, right? And the opposite goes, lower activation energy means a faster reaction. And so notice again, the products and the reactants are the same. They didn't affect the concentration of either one of them. The overall energy values of those are the same, and so that's what we mean by how the catalyst doesn't affect that, okay? Now, enzymes are biological catalysts. These guys are, they're just biological catalysts, right? So they are inside of our body, and it's actually really important, which I'll touch up on in a minute, that they do actually lower the activation energy. So the active site is basically, it binds an organic reactant, and that's called a substrate, okay? So for example, you may or may not have seen this, it's like a typical active site and substrate to represent a biological enzyme, and so that basically the substrate can only fit in an active site that is that shape. So that's pretty much how our body works, very simplistically. And that's why we have to have a particular three-dimensional orientation to work to bind to our biological enzymes, and that's why stereochemistry is important in chemistry as well, right? So for lab reactions, we do use simple reagents, and then a catalyst might be used, right? Depends on how much we have to heat a reaction. But for biological reactions, these are super complex reagents, or we can call them coenzymes, right? And obviously the body is super complex, and we try and reproduce it in a lab, but I don't know, it's really difficult. And so the biological reactions, they provide alternative mechanisms that make life possible, right? And why that is the case is because they reduce the amount of energy or heat that is released in a given reaction. It also reduces the amount of heat that is required for a reaction to move forward. Okay, so if we're looking at this particular energy diagram, the y-axis is energy. So if you got a high EA, that's really hot. If you got a moderately sized EA, that's still potentially hot, right? We said before that we have to heat chemical reactions depending on the energy levels. Some might occur at room temperature, but this pink line is basically my terrible drawing of an enzyme, a biological process where reactions taking place, and you can see that generally the energy, activation energy, is at least less than the organic reactions, right? And so looking over here, remember EA for most reactions is 40 to 150. Most of them are above 80 kilojoules per mole, which means that they will not occur at room temperature and they will require heat, okay? And so we just want to make sure that our bodies aren't overheated, and that's why I'm saying that the biological enzymes provide alternative mechanisms that make life possible, because if we didn't have those enzymes, we would have to heat the reactions way too much, and we would be too hot and die. All right, so this is me drawing some, this is morphine, okay? So you feel free to draw it or not, it's okay either way. The reason why I'm drawing it is because kind of thought about it for a variety of reasons, right? Morphine, terrible drug. Opiates are definitely an epidemic, pandemic, whatever. And there's a movie called Knives Out where naloxone actually came up. And it's also I saw an email recently that the school is providing training for naloxone distribution or whatever. And naloxone, is also known as Narcan. You might have heard of this before. And it's basically if somebody comes in and they are kind of unconscious, for example, then there's a variety of things that could be the cause of this, right? So they could have low blood sugar, they could have overdose on opiates or whatever. And if you know that they've taken too much of a drug like heroin or morphine or whatever, Oxycontin, etc., then naloxone is actually, I'm not sure if I would be getting this term right because, again, it's biology related, but it actually binds the same receptors as the opiate, and so I would think of it as a competitive inhibitor. So once it binds, it's not allowing the actual opiate drug to bind, like morphine or, again, heroin or Oxycontin, etc. And so if naloxone is binding it and the opiates can't bind it, then you're kind of allowing your body to process that drug and kind of get it out of your body or your system so that way you don't have those overdosing effects or things like that. Okay, so naloxone is obviously very similar in structure. I've highlighted the differences in red. Now this is why I find drugs structures very fascinating, because morphine, that will kill you very easily, and if you just change a few structures, obviously naloxone, maybe that would kill you too. I'm not sure, I don't know the details on that drug, but it doesn't have the same effect as morphine, even though the structure is crazy similar with only a few highlighted differences. But it's actually beneficial to kind of fight against an overdose, for example. And so I don't know, we could talk about this stuff all day, but I just really like the idea of like binding to enzymes or receptors, and the structures and how they are important, but also how subtle differences can affect their or can change the effects they have on the body. Fascinating stuff. But that's pretty much it. I guess this technically isn't related to enzyme activity. Well, it's definitely related to enzyme activity, I guess, but not increasing the rate of a reaction or anything like that. But it is just a fun kind of little ditty I wanted to throw at you, and how the structures of things can affect the way they kind of change our body. Okay, have fun with it. Bye.